Good day. Today I will be discussing about binary search tree, also known as BST, and its special type, which is the AVL tree. Before we go deeper, let us first understand what a tree data structure is. So, a tree is called a tree because it looks like a real tree. It has a top part, which is the root, and it branches down into smaller parts. So we use tree data structures to organize data in a way that is easy to search, insert, and delete. So the binary search tree, or BST, is commonly used in programming because it helps us find data faster compared to a normal list or array. Instead of checking values one by one, the tree already guides us kung asa ta moadto, pa left or right side, based on the value that we are looking for. So, what is binary search tree? A binary search tree, or BST, is a type of binary tree data structure in which each node contains a unique key and satisfies a specific ordering property. So, these properties includes that all nodes in the left subtree of a node contain values strictly less than sa atong node's value, and all nodes in its right subtree have values greater than the node's values. So, ang binary search tree daw is a type of binary tree, meaning each node can have at most 2 children. One left child and the other is one right child. So what makes it special is that it follows a specific rule. This rule says that for any node in the tree, ang all values daw sa left subtree must be smaller or gamay pa sa atong node's value. And all nodes sa atong right subtree must be bigger or greater than sa atong node's value. So for example, if we have a node with value 50, any value smaller than 50, like 30 or 20, should go to the left side or will go to our left sub tree or the left side of our tree. And any value bigger than 50, like 60, 70, or 90, should go to the right side of our tree. Because of this rule, searching becomes faster because we already know where to look at or where to look. So, here you can see an example of what a tree looks like. So, we have values 15, 9, 5, 10, 17, 16, 21, and 20. So, here, makita nato natay left subtree and right subtree. So, kung ang gingon ganina, the left subtree refers to all the nodes na mapangita or makita nato sa left side of a particular node. And makita ninyo diri ang value sa ato left subtree is R9, 5, and 10. So, these values is smaller than sa atong node nga 15. And on all values, makita nato in the left subtree are strictly less than the value of the node. So, on the other hand, we have the right subtree. So, the right subtree's values is 17, 16, 21, and 20. And we see that it is greater than or dako pa sa atong node 15. So, ningadto siya sa right side. So, the right subtree includes all nodes on the right side and their values are strictly greater than the node's values. So, here we have 15, our root node, or also our parent node. So, we have here the 9 and 17. These are the left and the right child of our parent 15. So, 5 is the left child of our parent 9, and you can see that it is less than our node, 9 node. So it goes to the left side. And the 10 is our 9's right child, and it goes to the right side since it is greater than 10 is greater than the node 9. So, importante sab nga ang left side or right subtree kay BST gihapon, meaning they follow the same rules. So, the height of our BST is 1, 2, 3. So, it has the height of its height is 3. So, child node or the parent node, child nodes is a node that comes directly below another node. So for example, here the child nodes of the parent 15 is 9, 17, and the child node of 5 and 10 is the child node of 9, current 9 is 5 and 10. Same goes here. The child node of the parent 17 is 16 and 21, and the child node of 21 is 20. So this relationship is similar to a family tree. Parents are above and children are below. So the parent or internal nodes. So internal node is any node that has at least one child. So, ang internal nodes here sa ato is 21 and the parent node is 17, 9 and 15. So, meanwhile, the leaf node is a node that has no children. So, it is located at the bottom sa atong tree. So, diri our leaf node is 5, 10, 16, 20 since it doesn't have any children. And leaf nodes are important because they mark the end sa atong branch, or in simple terms, internal node connect the tree and leaf node finish the structure. So to summarize this, sa akong gipang sulti ganina, the properties of binary search tree: for any node X, the left node or the left child and all its descendants have lower values sa atong X or the node, and the right child and all its descendants have higher values than the node. Also, both the left and right subtree must also be binary search tree. So these properties must also be followed to maintain the correctness and efficiency of the BST. Here we have the AVL tree. So what is AVL tree? So ang AVL tree daw is a self-balancing binary search tree where the difference between heights of left and right subtrees cannot be more than 1 for all nodes. This difference is called the balance factor. And the balance factor is calculated the height of the left subtree minus the height of the right subtree, and its equal is dapat dili mo gawas sa negative 1, 0, and 1. So it means that by AVL tree automatically maintains balance as values are inserted or removed in a normal BST. If values are inserted in sorted order, the tree becomes skewed or unbalanced, making the searching slow. So the AVL tree solves the problem by making sure the tree stays balanced. So the balance factor. The AVL tree uses something called the balance factor. The balance factor is computed using the formula. Balance factor equals height of left subtree minus the height of right subtree. The allowed values for the balance factor are only negative 1, 0, or 1. And if the balance factor goes beyond this range, the tree performs rotations to restore balance. So, conclusion, a binary search tree is a data structure that organizes data using the rule. Smaller values goes to the left and the larger values go to the right. The AVL tree is a special type of BST that keeps itself balanced to ensure fast operations. Understanding this structure is very important because they are widely used in programming for efficient data handling. So unbalanced binary search tree. So makita ninyo na tayo mga values nga gi-insert 1, 2, 3, 4, 5, 6. So paano nato nalaman yung unbalanced siya? We perform the balance factor. So the height of the left subtree is 0 and the height of the left subtree. So if i-calculate na, ang mugawas is negative 5. So negative 5 is dili siya exactly negative 1, 0, or 1. So it means balance siya or ni goes beyond the range. So if this tree is skewed and unbalanced, so if mag-search ra niniyag pangita na to ang values, is it makes the operation or slow or mahinay siya. So diri have this code or program. This code is an example sa insertion. So inserting nodes into an AVL tree and making sure the tree stays balanced. So sa taas, at the top we include stdio library.h and stdio.library.h. So, stdio.h kay para sa printing gamit ang printf, and stdio.library.h kay para sa memory allocation gamit ang malloc, which we need para makakreate og new nodes. So, diri we define the node structure with struct node. So, each node has a key, which is the with value it stores a left pointer, a right pointer, and a height. So, the height is very important kay mao ni ang mag-decide if balance pa ang tree. So next we have the height function. The line if n is equal to null, it returns 0. Mag-return na siya, meaning kung wala yung node sa spot, 0 ang height. Otherwise, it returns the stored height. So the max function just compares two members or two values and returns the bigger one, which we use when updating heights after insertion or rotation. The new node function is for creating a node. First, we allocate memory using malloc, then assign the key. The left and right pointers are set to null, kay wala pa siya children. And height is set to 1 because it's a leaf. Then we return the node so it can be inserted into the tree. After that, we have rotation. Function, right rotation and left rotation. These rotations are used kung ang tree dili na balance. For example, sa right rotation, we take the left child of the unbalanced node and make it the new root sa iyang subtree. We also save temporarily ang right subtree sa child para dili mawala. Then we adjust the pointers ug gi-update ang heights. So ang left rotate is the same pero sa opposite direction. So the get balance function calculates the balance factor, which is height sa left subtree minus height sa right subtree. If the node is null, balance factor is 0. Kani, it help us know kung left heavy or right heavy ang atong tree or balance ba ang atong tree. So we know if kinahanglan nato og rotation. The insert function is the main part. Main part. First, it does a normal BST insertion. Ang line, if node is equal to null, kay nag-check kung naa siya'y empty spot. Og yes, if yes, it creates new node. If key is less than the current node, we go left, and if key is greater than or ang atong node is greater than the current node, we go right. So after insertion, mag-update ang height using max sa left and right plus 1. Then i-check ang balance factor. If it goes outside the range, -1 to 1, the tree is unbalanced. So we have 4 cases, left, and right, left, right, and right, left. So each case has its own rotation to bring the tree back to balance. So ang pre-order function, kay i-print niya ang tree. So the root first, then left and right subtree. So ang int main function is nga na siya sa bottom or duwa siya sa sa first is i-need pa man siya i-define before they are called. So the main starts sa empty tree with root null. Then insert values one by one. Nag-insert siya 10, 20, 30, 40, 50, and 25. Kada insert sa atong tree, kay ang AVL, i-check niya kung balance ba ang atong tree ug dili rotation is needed. So at the end, the pre-order or root prints the tree and tells the program it finished successfully. So diri makita nato nga giunsa sa AVL tree pag-balance or kung mag-perform tag-balance factor is ato tree is balance. So nag-perform ang AVL tree og mga rotation diri So basically nag-show giunsa pag-maintain sa balance sa AVL tree and why rotation and heights are important, and how all the function works together para efficient ang insertion diri So sa next is kung giunsa pag-delete sa AVL. So the this AVL program supports both insertion and deletion. So the main is naa sa wala sa pinakaunahan, nasa last or nasa sa bottom, wala siya sa igbaw, kay i-define una before siya gamiton. So ang main nag-call sa insert, delete node ug pre-order. Sa first or top sa code, nag-define siyang struct node. Kini nga structure nag-represent sa usa ka node sa AVL tree. Ang key mao ni ang value sa atong node. Ang left ug right pointers nagtudlo sa left ug right children sa node. Ang height variable mao ni ang pinaka-importante nga part kay mao ni ang basean sa pag-check kung balance ba ang tree. Unlike sa ordinary BST, ang AVL tree kinahanglan jud mag-store og height sa matag node. Ang height function gigamit para kuhaon ang height sa usa ka node. Kung ang node kay null, mobalik siya og 0. Ug ang importante ni aron malikayan ang segmentation o para sakto ang computation sa balance factor. Ang int max is kay helper function na siya para nga nagbalik sa mas dako nga value sa duha ka integers. Gigamit ni siya sa pag-compute sa height sa usa ka node. So ang new node function mao niyang responsible sa pag-create og bag-ong node. Dinhi gi-allocate ang memory gamit ang mga lock. Ang key gi-assign sa node ug ang left ug right pointers gi-set ngadto sa null. So ang height gi-set sa 1 kay sa initial stage ang bag-ong node kay leaf node paman ug ang height sa leaf node kay always 1 sa AVL tree. Sunod na ata sa rotation function, which are right rotate, left rotate. Kining rotations mao gyud di ang reason ngano ang AVL tree is self-balancing. Ang right rotate gigamit ni siya kung ang tree kay heavy ra siya sa left, meaning taas ang left sub-tree kaysa sa right sub-tree, and left rotate is gigamit kung ang tree kay right heavy. During rotation, giusab sa AVL tree ang link between nodes kay aron mabalik ang balance ug human ana gi-update usab ang height sa mga naapektuhan nga nodes. So importante sad nga gi-update ang height kay nag-usab man ang structure sa tree. So ang get balance function nag-compute sa balance factor sa usa ka node pinaagi sa formula nga height of the left subtree minus the height of the right subtree. Kung ang balance factor mo exceed sa +1 or -1, pasabot ana nga unbalance na ang node ug kinahanglan na og rotation. Ang insert function nagsugod sa AVL insertion process. So una gihimo ang BST insertion. Kung null ang node, mag-create siya og bagong node. Kung ang key mas gamay sa nodes key, adto siya sa left sub-tree. Ug kung mas dako, adto siya sa right sub-tree. Human sa insertion, gi-update dayon ang height sa current node ug gi-check ang balance factor. So, depende sa klase sa imbalance, left-left ba, right-right, left-right, or right-left. Mao ni ang part nga nag-ensure nga balance gyapon ang tree after sa insertion. Ang mean value node function gigamit sa deletion process kung ang node nga i-delete kay adunay 2 children. This function mangita sa in order successor, which is ang smallest value sa right sub-tree. Mao ni ang safest nga value ipuli sa node nga gi-delete aron ma-preserve ang BST property. Ang delete node function mao ni ang pinaka-complex nga part kay sa step 1 gihimo una ang standard deletion. Kung ang key mas gamay sa root nato, i-search ang paniya ang left sub-tree. Kung mas dako, adto siya sa right sub-tree. Kung pareha ang key, mao na ni ang node nga i-delete. Dinhi gi-handle ang 3 cases. No child, 1 child, o 2 children. Kung walay child, simply gi-free ra niya ang node. Ug kung ang 1 child ra, gi-copy ang child ngadto sa current node. Kung 2 children, gi-copy ang in-order successor ngadto sa current node o gi-delete ang successor. So diri sa int main nag-insert ta og values 9, 5, 10, 0, 6, 11, -1, 1, and 2. So, diriya makita nato kung giunsa sa AVL 3, kani siya mao na ni ang kanang balance factor ay balance AVL 3. So, nag-perform ni siya og mga rotation diriya, while ang sa kani, if makita ninyo diri root daw nato nga 9 is delete node. So i-delete daw ni delete root is delete node equals delete node, root is 10. So meaning ang root 10 ay ang node 10 is i-delete daw. So, ang AVL 3 is nag-ensure nga ang height difference sa left ug right sub-tree sa matag node dili mo lapas og 1. So, balik when the value 10 is deleted daw, using the delete node function, the program first perform binary search tree deletion. Since ang node 10 kay adunay 1 child which is 11, ang node 10 gi-remove o gi-replace sa iyang child. So, mauna ni puli ang child sa 10 sa iyang position. However, tungod ani nga deletion, nausab ang height sa right sub-tree nato sa node 9. Ug this causes the tree to become unbalanced. So, as gi-update niya ang height ug gi-check ang balance factor sa mga nodes and rotation are applied to fix the imbalance. So, after rebalancing nato, the new root of the AVL tree becomes 1. Its left child is 0 and still has -1 as its left child. On the right side, ang node 9 has become the right child of our new root 1. and 5 as its left child, and 11 as its right child. While ang node 5 still has children which are 2 and 6. So, these final structures confirm nga even after deleting a node, ang AVL tree remains balanced. Og ang binary search tree property kay gi-preserve gihapon. So, that's all for my topic. Thank you very much for listening.